Hello, everybody. This is Sunday. It's January 23rd, and we are moving into week 3 of our online astronomy course. Before I get started, I have a few pieces of astronomy news for you. And the first one has to do with the James Webb Space Telescope. Tomorrow, the telescope will be making its final firing of its thrusters, and that will put it in its final location to make observations. So this is the last critical thing. It has to do, it will happen tomorrow around noon Utah time, and that will be it. From then on, it will take several months for them to really focus the mirrors properly, for the telescope to cool down. And this is just wonderful, great news that it's made it all the way there with no problems. So that journey is going to come to an end, to its final spot tomorrow around noontime, our time. Also, I can tell you about, you may know that there have been a lot of other planets around other stars that have been discovered. As of today, I think there's over 4,900 other planets that we know of. But just this past week, they've discovered the first moon around an exoplanet. Now, it's really hard to find, an exoplanet because they're so small and they only shine by the reflected light of their parent stars. And so it's really hard to see an exoplanet, and finding them is really a challenge. And so you can imagine how difficult it is to really identify a moon around an exoplanet. That's happened for the first time this past week. It hasn't been confirmed yet. Still has to be confirmed, but it's looking like this is going to be a pretty sure thing, and it's be very exciting for people who study planetary systems around other stars. All right, well, let's take a look ahead and find out what we're going to be encountering this week in Module 3. Well, this is where we learn some of the laws of nature that astronomers use in order to describe how stars and planets and galaxies work, how they move. And these laws of motion were first described by Isaac Newton. Now, Isaac Newton, probably the greatest of the physicists who ever lived, one of the greatest minds ever, was born on Christmas Day in 1642. And right here behind me, you can see the house that he lived in. It's in Woolsthorpe, England. We were there about 10 years ago, so we dropped by. He wasn't home, he's been gone for a while, but still we could drop by and see the house that Isaac Newton lived in. And Isaac Newton was famous for discovering, or first describing, how things move. And he came up with 3 laws of motion that talk about how things move. And it's not like people knew things could move, obviously, before that, but they didn't really understand how forces worked. Now, you know what a force is. If I push on you or I pull on you, pushing and pulling is just a force. But people thought you had to keep pushing on something to keep it moving. I mean, that's a common thing. You have to keep pushing on something to keep it moving. But Newton says, no. That's not true. That's not what forces do. You don't need forces to cause motion, to keep something moving. What forces do is that they change something moving. They change how objects move. And so, says Newton in his first law, if an object is at rest, it remains at rest. And if an object is moving, it will keep on moving. Unless, he says, an unbalanced force acts on it. And so if I start pushing a box across the floor, I just, shove it and I let it go, that box will come to a stop because the force of friction slows it down. So the force of friction is changing the motion of the box. Now, if I just want that box to keep moving, I have to keep pushing on the box. And if I push just as hard forward as friction, the force of friction is pushing against my force. If my pushing force and the frictional force balance each other, then the box moves at a constant speed, excuse me, and there's no forces acting on it. So that's what Newton says. His first law says that an object in motion stays in motion unless an outside force, an unbalanced force, acts on it. And so, for instance, if I have an object and I'm just looking around me to find something, and I'll just use my calculator here. So if I hold out my hand, there it is. Sort of hard to do here. There, I'll just do it like that. If I hold out my hand and I put the calculator on my hand, then the calculator is staying at rest. Now, gravity is pulling down on that calculator. But why doesn't it fall? Well, because my hand is holding it up. And those two forces, the downward force of gravity on this calculator and the upward force of my hand, are exactly in balance. And so the calculator's at rest and it remains at rest. But if I were to remove my hand really quickly, the calculator now has an unbalanced force acting on it, the force of gravity, and so the calculator falls. So that's Newton's first law. Okay. The second law talks about how forces produce a change in motion. How much force do you need? Well, you know, if you've ever tried to push somebody, say you have, you're going to push a car, and there might be a really light small car, and there might be a really heavy SUV, and you push on those with the same force, which one's going to speed up more easily? Well, the small car is going to speed up more easily if it's just, you know, it's in neutrals, and you're just pushing it so you can push it along. The small car will speed up more easily than the large car. And so what's the difference between the small car and the large car? It's their mass. And mass is an important concept. It's the amount of matter that's in the object. And so it's the amount of stuff that's in the object. And so if I push on something with a small amount of mass, it will speed up a lot. But if I push on something with a lot of mass, that massive object will not speed up very much. So Newton's second law talks about how forces and masses produce acceleration. So you'll be learning all about that. Newton's third law is probably the most mysterious, but it's something you've encountered before, because if you've ever been trying to crowd through get out of a room, a large number of people, like at a concert or a basketball game or something, you're trying to get out a door and everybody's pushing everybody else, you know, they're pushing you from behind, you're pushing back because you don't want to, you don't want to fall over. And so this is sort of like the law of crowds is Newton's third law. It says, if I push you, you push me back just as hard. If I pull on you, you pull on me back just as hard. You can't help it. And you can demonstrate this with just a little rubber band. So here's a little rubber band. I'm going to put it around my thumbs. I'm going to stretch it out. And you can feel the force on each thumb. And you might notice that if you change the stretch or you move your thumb around, so you might think that, oh my gosh, if I'm moving this way, then one thumb is pulling more than the other one. But you can feel with the rubber band that you always have the same pressure on your thumbs. You always have the same force on your thumbs. And that's what Newton's third law says. If I push you, you push me back just as hard. So there are Newton's 3 laws of motion. And today astronomers use them to describe the way everything moves. It describes how moons move around planets. It describes how planets move around stars. And it describes how stars move around the center of galaxies. It is amazing. It is how we were able to pilot the James Webb Space Telescope out to this specific point in space and get it there so it can gently stay there and make its observations. So thank you, Isaac Newton, for these wonderful laws of motion. Now, Newton had one more idea too. Well, actually, he had a ton of ideas, but the most important law for us in astronomy is his law of universal gravitation. And the law of universal gravitation, the word universal means that it applies to everything that has mass. And Newton's law of gravity says that everything that has mass attracts everything else that has mass. It means that if you're sitting watching this and there's somebody, sitting beside you or on the other side of the room, that both of you are attracted to each other because of your mass. You're attracted to the mountains, maybe outside your house, because of the mass of those mountains. But what are we attracted to most? Well, what's the most massive object in our immediate vicinity? And it's the Earth itself. We're all attracted to the center of the Earth that we live on. And so Newton supposedly learned about this when he saw an apple fall from the tree. And you can see some apples on this apple tree here in Newton's yard. And supposedly he was sitting inside the house here. He was sitting inside his house in one of these rooms looking out the window. And he saw the apple fall. And then he looked up at the moon and he wondered about the moon. What holds the moon in its orbit around Earth? And supposedly that inspired him to invent or come up with his law of universal gravitation. And in fact, this apple tree right here over my shoulder is the apple tree that Newton's apple fell from. This tree is over, let's see, it would be 450 years old now, over 450 years old. And you might think, how can that be the same apple tree? Come on. But what happened is that it blew over in a storm and the roots survived and then they grew back to form an apple. And there's an official plaque here, that says this is the apple tree that that produced the apple that Newton watched fall and came up with his law of gravity. So you'll be learning about all this in Module 3. These laws are expressed in the language of mathematics. So there's some calculations to be done in your homework quiz for Module 3. But remember, just go to the module introduction, the introduction for Module 3, and I have worked examples of all the things you'll be learning. And Newton's law of gravity allows us to figure out the masses of objects. I mean, how do we know how massive the sun is? How do we know how massive stars are? How do we do that? And you'll find out that the key to that is Newton's law of gravity. So before I go, let's take one quick look in the sky. And so I'm going to bring up Stellarium again. Here we go. Here's Stellarium. I've set this for, this is actually going to be Tuesday night, January 25th. This is what you'd see if you were looking outside around 9 in the evening. And in fact, it was yesterday I looked outside our door. Our door faces a little bit to the east. And so I looked out and looked to the southeast, and there was Orion in the night sky, my favorite winter constellation of Orion. And we'll be talking about Orion a lot because there's so many interesting things happening in that constellation. Now, if you look out tonight, you may look around and say, where's the moon? You know, it's not a new moon yet. In fact, on the 25th is going to be the third quarter moon on Tuesday. And to find the moon, we're going to have to go forward in time. So we're at 9 o'clock now. So here's 10, 11, it's midnight now. And so we're just going to go forward until it's about 4 or 5 in the morning. So you have to go to 5 in the morning to see the moon. And you can see we're getting close to the sun here. It's close to sunrise. And so the moon is approaching the sun. It's moving a little bit more east every day. And right now it's the third quarter moon. As you can see, if I zoom in to the moon's position, there we go. And there's the third quarter moon. So go out, if you're working on your moon phase, your calendar of moon phases for observing project 1, the extra credit observing project, and you've been wondering where the moon is, well, that means you're going to have to get up a little bit early to see the moon today or the next couple of days. But I hope you learn about, hope you enjoy learning about Newton's laws of motion, about his laws of gravity, because these are the main tools that astronomers use to understand how the universe works. And I'm going to be telling you some amazing things about the universe. And I want you to understand how it is we, just staying here on Earth, can find out about all this. So enjoy learning about that. And I will look forward to seeing you next week. So until then, have a great week. Bye-bye.